Assalamualaikum. We are from Group 3. Group 3 consists of me, Muhammad Isharuddin, and Wanu Ikmil and Teshin I. So today we are presenting our assignment 1. For introduction, the most important aspect of this project is development of ANN, which is artificial neural network, to predict student academic success. It addresses the limitation of traditional grading by analyzing nonlinear factors like mental health, study habits, and environmental variables using a multi-layer perceptual MLP architecture. The system accurately classifies students into a pass or fail categories. A key part of the work involved comparing different model configurations, specifically RELU and 10 activation function to find the most reliable predictive setup. For the objective, we have three key points, which is design and implementation, data preparation, model optimization, performance evaluation. For design and implementation, to build an artificial neural network and using a multi-layer perceptron (MLP) architecture tailored for student classification, data preparations to perform feature engineering and data normalization to ensure high quality training data, model optimizations to develop and compare at least two different A and N setup by adjusting parameters like hidden layers, activation functions, especially RELU and time for performance evaluations to rigorously test the model using metrics such as accuracy, precision, and recall while visually comparing predicted outcome against actual result. Next is data acquisition and pre-processing, which is data source. The project utilized an exam score prediction dataset for quantitative metrics and the student mental health dataset for qualitative dimensions. So next is synthetic generation. A synthetic dataset was generated to mimic real-world characteristics while ensuring consistency for the analysis. And next is encoding. Categorical variables, example gender, horse, were converted into numerical form using label encoding. Next is normalizations. All numerical features were standardized using a standard scalar to improve model training and convergence. And lastly is data splitting. The data was divided into 70% for training and 30% for validations, which stratification to keep the target classes balanced. So this is A and N model architecture, which is we have two distinct A and N, which is TensorFlow and Keras. So the feature is hide the layers, activation function, optimizer, output layers. So model A and B, which is RLU enhanced for hard layer, it's have two layers, and while model B is three layer, and the activation function is RLU 10 for set for model A and model B is 1011. For optimizer, the model A is AGD, while model B is Adam 13. For output layer, for model A is softmax, and then softmax 14, and model B is softmax 15. So the lastly is training and evaluation strategy. First is loss functions. Both models use categorical cross entropy to measure prediction errors. Next is overfitting prevention, which is training included early stopping, halting if validation loss stop improving, and the learning rates reduction callbacks. The next is evaluation metrics, which is performance was assessed using accuracy, precision, recall, F1 score, and confusion metrics, and lastly, visualizations, which is across or loss curve and side-by-side plot of predicted versus actual result were generated to verify the model reliable.
Hi, Assalamualaikum. My name is Wano Ikmil Haji. So I will continue for the model A, which is exam score prediction. So I will start for model A, which is first looking at model A using ReLU. We can see that the training accuracy increased steadily and reaches a high value, while the validation accuracy stabilized at around 60%. This gap indicates that the model learns well from the training data but struggles to generalize to unseen data, suggesting overlifting. From the confusion matrix, model A performs well in predicting the high mental health category. However, it fails to correctly classify the low and medium categories, which are often misclassified as high. This is also reflected in the classification report, where only the high class show meaningful precision and recall. This limitation is mainly due to class imbalance and the small data size. Now, we're moving on to the model B. Using the 10H activation function, we observe a modest stable learning pattern. Both training and validation accuracy reach around 80%, indicating better generalized compared to model A. The confusion matrix for model B show improved classification, especially for the medium mental health category, where all samples are correctly identified. The high category also maintaining strong performance, while the low category remains difficult due to having a few samples. Overall, Model B outperformed Model A, achieving higher accuracy and more balanced classification across categories. This comparison highlights that the choice of activation functions plays a significant role in the model performance, especially while working with limited and imbalanced data.
Now I will discuss the performance of Model A, which uses the ReLU activation function. Overall, Model A demonstrates stable and reliable performance in classifying exam scores. From the accuracy graphs, we can see that the model learns quickly with training and validation accuracy converging within the first 10 epochs. This close alignment indicates good generalization and minimal overfitting. The model achieved its best performance at epoch 33, reaching a peak validation accuracy of approximately 72.5%. Based on the confusion matrix, model A is particularly effective at distinguishing between the highest and lowest performance levels. There are almost no cases where excellent students are misclassified as failed or vice versa. Most errors occur in the pass category, where some excellent and failed students are predicted as pass, indicating difficulty around the boundary of the middle class. Overall, the classification report shows an accuracy of 72%, with the highest precision of 0.76 for the excellent class. Recall is consistent at 0.72 across all categories, and F1 score range from 0.71 to 0.74, confirming that Model A provides a strong and balanced baseline for exam score prediction. Next, I will explain the performance of Model B, which uses the TNH activation function. From the accuracy curves, Model B reaches its peak performance relatively early. The highest validation accuracy is achieved at epoch 18, stabilizing at approximately 72%. After this point, the training accuracy continues to increase towards 73%, while the validation accuracy begins to fluctuate and slightly decline. This divergence indicates that the model reaches its optimal learning capacity and shows a tendency toward overfitting if training continues beyond the optimal epoch. Looking at the confusion matrix, Model B demonstrates strong separation between extreme performance levels. There are only 7 cases where excellent and failed students are misclassified as each other, showing effective distinction between top and bottom performance. However, the model shows a noticeable bias towards the pass category. While it correctly identifies 2,048 pass students, it also observes a considerable number of misclassified excellent and failed cases, indicating difficulty with borderline students. From the classification report, the overall accuracy remains at 72%. Model B performs especially well for the fail category, achieving the highest precision of 0.77, meaning its failure predictions are highly reliable. It also records a higher recall for pass at 0.75, showing better coverage of passing students. With a web F1 score of 0.72, model B proves to be a reliable classifier, particularly effective in identifying students at risk of failing while maintaining broad sensitivity across the dataset.
Overall, this project demonstrates the successful development of an intelligent control system using artificial neural networks to predict both student academic performance and mental health status. By implementing two different multiplayer perception architectures, the system shows the NN model are capable of capturing non-linear relationship between socio-economic factors and student outcomes. Starting with model A, which use the ReLU activation function, the model shows stable learning behavior. The training and validation accuracy covers within the first 10 epochs, indicating a consistent learning without sudden fluctuations. In comparison, model B, which used the Tanha activation function, achieved its peak performance earlier. However, when trained beyond the optical epoch, it showed a slight tendency toward overlifting, highlighting the importance of proper epoch selection. For exam score prediction, both models achieved an overall accuracy of 72%. However, model B performed better in identifying students at risk of failing, achieving a precision of 0.747 for the fail category. When up, when applied to the student mental health classification task, the limitation of small data sets becomes evident with only 10 samples. The ReLU model showed irregular accuracy pattern and strong bias toward majority class. In contrast, the Tanhan-based model B produced more balanced result, achieving 80% accuracy and successfully identifying medium stress level, which the ReLU model failed to classify correctly. In conclusion, with an model are effective tools for educational prediction. Their performance is highly dependent on data size, as well the careful selection of activation function and optimizers to minimize overlifting and improve reliability.